So Dyer's been a busy place, and we just got through summer camps, and I act like I'm really exhausted by that, but actually Dr. Billy ran the science camps and our volunteers that you saw in the front. So all I did was the work behind the scenes, but God bless teachers. It was 2 weeks for us. Great kids, but boy, it takes a lot out of you, doesn't it? Yeah. So we have one of the best summer science camps, I think, in the world. So rising 5th, 6th, 7th, and 8th. Next year, be sure and send any kids that you know that fit that age bracket our way. So I want to announce a couple things that are in the works. They're not formalized yet, but Dyer was built in 1953. So, well, it was built in 1952 and dedicated in 1953. Since 1953, our dome that houses the telescope has not been painted. It's had a few touch-up coats, but it's time to be stripped down and sandblasted and recoated. And I'm telling you that because we may need help with that. We're going to bring in a 100-ton crane, and we're going to lift it off the building, and we're going to make it a community event. We're hoping it's going to happen in October. I wanted to get a Huey helicopter to lift it up, but I couldn't get it approved. And the Vanderbilt helicopter is too small. So anyhow, that's one of the neat things we're going to do. The other thing, did you notice our carpet when you walked in? Some people love it. Most people do. Some hate it. But it's custom designed, and it was printed in 2003 when we renovated. We're going to redo our carpet. And you may not think that's a big deal, but one of the things we're going to do is we're going to print our carpet again, but we are going to take the original celestial globe that was purchased in 1875 that's got the celestial heavens on it and the map, and we're going to photograph that in sections and do sections of the globe on the carpet. Should look really, really cool. So that may be another thing we need help with. Not laying the carpet, but donations, of course. And with the dome, not lifting the dome, you know how that goes. So Dr. Billy Teets came to us in 2006 as a graduate student, and quite a bit younger, 2006. Seems like a long time. He was just a little kid at that point. He was always an astronomy enthusiast and on the astronomer track, heavy in physics. So he came to Vanderbilt and instantly volunteered out here. And he was such a hard worker, diligent guy, very, very smart, that we hired him to work with us part-time at first. So when he came to us in 2006, we were building the Star Chamber. Have any of you seen that down behind the house? An art piece that we built in 2006. It's, I think, 30 truckloads, triple axle truckloads of stone that hand stacked to make a camera obscura. So you walk inside and you see the heavens projected, the sky projected down on the walls and on the floor. So it's been a very, very successful piece, but one of his first jobs was moving stone. So he probably didn't expect that when he wanted to work here and volunteer for astronomy. One of the other jobs that we remembered when we were talking about it today was we had a skunk that would get into the garage. So he had to chase the skunk out. So that was the first experience with Dyer's, moving rock and chasing skunks. Anyhow, he got his PhD here at Vanderbilt in 2012, and he has become really, I would say the heart and the soul, but that leaves no place for me. He's the heart. I'm hoping I'm still a little bit of the soul. But almost everything that happens around here anymore, Dr. Billy directs. He built the model out front in the display case that is not working now because we got a lightning strike 3 weeks ago. And so we've got to replace a few things. But he redid the telescope upstairs, completely redid it this winter, and it looks absolutely phenomenal. He redid the DeWitt telescope from 1937 that's above my head, and has just put together all these incredible programs. He is really the heart and soul of our summer camps and a lot of the outreach we do. And I'm really, really proud to have him as a colleague here. He's one of the greatest guys in the world aside from that. So he's going to tell you about the eclipse. Dr. Billy Teets.
All right. Well, thank you very much, Rocky, for that wonderful intro. Kind of brought a little tear to my eye. But yeah, Rocky's a wonderful person to work with. Nathan, all the people that work here are awesome. So it's been a blessing to be a part of this for now, 11 years. So I hope to keep being up here for many, many more years as well. So tonight's talk, we're going to be focusing on the eclipse. So who in here did not know about the eclipse up until maybe a few months ago? Okay. No, I mean, don't be bashful. I'm not going to call you out, okay? All right. So good. A lot of people have just learned about the eclipse. I was talking to somebody last week that hadn't even heard of it yet. So people are constantly learning about this really spectacular event that we're going to have an opportunity to see this August. So the point of this talk tonight is to try to inform you as much as I can and not drag it out too much, but give you some background on eclipses so that you really appreciate what you're seeing. Some information about where to be, when to be in order to see the total eclipse, which is the really special part of this eclipse, and also, most importantly, how to safely view the eclipse. First off, did everybody get one of these little sheets as you came in? Okay, I think everybody did. Has information about the eclipse. Everybody got one? Yes. All right, good. I don't have to talk tonight. No, I'm just kidding. No, that's the quick and dirty what we're going to talk about tonight. So I'm going to give you some more details. I'd really like to start out with this image. This was from a 2015 eclipse up in Norway. You can see the nice ice fields out here, the guys in the trucks out here. But this is not a photoshopped image. This is basically what you would have seen if you were out on that ice field with those folks. Okay, so this... folks that I talk to that have seen numerous total solar eclipses say there's nothing else like it, and they'll travel the world just to see these events that only last for a few minutes at most. Okay, so that tells you something right there, that this is something really special. So again, the outline tonight, we'll start out with a little bit of background on the different types of eclipses. I'll even touch a little bit on lunar eclipses because in a way they kind of go hand in hand with solar eclipses, and we'll mention why. Definitely give you some information about the August 21st eclipse, especially times, where you need to be, and some things that you're going to want to look for during the total eclipse, and also during the partial eclipse. And then finally, again, this is the most important part, how to view the eclipse safely. Because again, we're going to be looking at the sun, and if you don't know how to look at the sun correctly with the right type of equipment, you can severely damage your eyes, if not blind yourself. So let's do a little bit of background on eclipses. So I've got two diagrams here. The top diagram is showing the configuration of the sun here on the left, the Earth, and then the moon for a lunar eclipse. And then down at the bottom, a little bit harder to see for the folks in back, unfortunately, we have the setup for a total solar eclipse here. So there's a couple things to note. First off, I want you to note this little note here. The distances and the sizes are not to scale. We'll talk about that more in just a second. But for a solar eclipse, you obviously have to have the moon in between us and the sun in order for it to be able to cast a shadow. It'll cast two shadows. This larger outer one, and I'm going to highlight it up here as well in our lunar eclipse diagram, which is a little bit easier to see. There's an outer shadow that is being cast by a body that's being illuminated by the sun. That outer shadow, the larger shadow, is called the penumbra. If you are in the penumbra, then you're going to see the sun partially obscured by whatever is doing the obscuring. So, and for a lunar eclipse, if you were standing on the moon looking back towards the sun, you would see the Earth partially obscuring the sun if you were in the penumbra of the Earth. If you're in the the penumbra of the moon during a solar eclipse, as most of North America will be, actually all of North America will be on August 21st, you will see a partially obscured sun. Right? Solar or partial solar eclipses, where you're seeing just a part of the sun blocked out, those are not particularly rare. I've seen quite a few in my day. They typically will be seen somewhere on the Earth about every 5.5 to 6 months. But the real important part is if you're in this inner shadow. This is what we call the umbra. Okay? And you'll notice, especially when you look at this diagram up here, the umbra is a smaller shadow. So that's going to be important because you're going to have a smaller viewing area in which to be inside the umbra, where you're going to see the sun completely obscured by the earth, or by the moon. Okay? Now, let's come back to this whole deal about things not being to scale. In these diagrams, the earth and the moon, that's actually a pretty good scale representation. So the moon is about 4 times smaller in diameter than the earth. The sun is obviously a lot larger than this. The sun is about 100 times the diameter of the earth here. But the distances are not scaled correctly. All right? So let's do a little demo here. So I've got a meter stick. At one end, pretty much at the very, very end, I've got an earth. It's 1 inch in diameter. And then I have my little moon here, 1/4 of an inch in diameter. All right? Pretty hard to see if you're in the back there, so I apologize for that. If we were going to set up a scale model, our sizes are already scaled correctly, but if we wanted to separate them at the right distance, how far away would our moon have to be from our Earth? So I heard the actual distance. Okay. So if we scale it down, how many inches from the Earth would the moon have to be? Anybody have any guesses? Any brave souls with any guesses? I heard 31. Anybody think larger, smaller? I heard maybe a fraction of an inch. I heard 17. So on average, okay, I heard 25. Not a bad guess, because on average, the moon is about 30 inches away from the Earth on this scale. Now, because the moon has an elliptical orbit, it changes its distance, but it'll go from anywhere from 28 to 32 inches away from the Earth. Okay? So a lot of people, when they set up this model, they think, okay, it's going to be right up here, which is not a bad guess. I mean, looking up in the sky, it doesn't look like the moon's that far away, but it's deceptively far away. Okay? On this scale, how far away would our sun be? A little bit harder. Okay, I heard downtown Nashville. It's definitely not going to be on the meter stick, right? All right. So I heard downtown Nashville. Not a bad guess. Anybody else?
Williamson County.
Williamson County. Okay, we're heading in the opposite direction now. Maybe at the other end. So way out here. So it'd be about 1,000 feet from us. Okay, and the diameter would be about 9.5 to 10 feet. All right, so that's a fun little demo just to give you an idea. Now, in order for the moon to be able to cast a shadow on the Earth, if the sun is over to my right here, to your left, and it's casting parallel light rays, if the moon is way up here or way down here, then the shadow of the moon is going to miss us. And that is the reason why we don't have solar eclipses that often. Okay? So let me show you a little diagram. So if you couldn't see it from the back, here's our scale Earth to Moon up there, separated by about 240,000 miles in reality. But when we were talking about the requirements for an eclipse, we had to have, for a solar eclipse anyway, we had to have the moon coming in between the Earth and the sun. Or in other words, the moon is going to be in a new moon phase. That's the only phase in which we can have a solar eclipse, whether it's partial, annular, or whatever. Okay? For lunar eclipses, for the moon to pass in the shadow of the Earth, it's got to be in the full phase. It's got to be on the opposite side of us from the sun. Okay? Now, we have a new moon every month, and we have a full moon every month, but we do not have eclipses every month. Okay? We have these periods known as eclipse seasons, and they happen about every 5.5 to 6 months. And that's because of that alignment requirement for us to have the shadow of the moon cast across the Earth. So here's an exaggerated view of the orbit of the moon and the apparent orbit of the sun around the Earth. Obviously, we're the ones going around the Earth, or around the sun, but from our viewpoint, it looks like the sun is going around us. Okay, that's what humans had believed up until about, the 1800s or so. Some people still believe that today, but that's fine. But if we were to kind of just draw a little diagram showing the moon orbiting the Earth here, and maybe the sun orbiting the Earth here, if the two orbits were aligned so that they basically laid on top of one another, then we would have a solar eclipse at every new moon phase and a lunar eclipse at every full moon phase. But the orbit of the moon is tilted with respect to the plane of our orbit around the sun. Okay? So this angle in between this red orbit of the moon and the apparent blue orbit of the sun, that's about 5 degrees. It's not that much, but it is enough to keep us from having eclipses that often. But you'll notice that there are points that we call the nodes, where those two orbits intersect. So if the sun and the moon are both at a node, then we can have an eclipse. And that happens about every 5.5 to 6 months. Okay? Now, eclipses aren't that rare. Here's a view of, so this is a Mercator projection of the Earth with eclipse paths for total eclipses, or these things called annular eclipses, which we'll talk about in a moment, from the years 2001 to the year 2020, or to the year 2020. So here's our path of the August 2017 solar eclipse, going right across the U.S. there. There was an annular eclipse that went through the western portion of the U.S. back in 2012. But the thing to take away from this is that there were a lot of eclipses in those 20 years. Now down here it looks like the eclipse paths were really wide, but that's just an effect of that Mercator projection. It always makes Antarctica look humongous, always makes Greenland look as big as the U.S., even though it's much smaller. But again, the point here is that there were a lot of eclipses that occurred in that 20-year period. And just for reference, in case you unfortunately missed the total solar eclipse this year, in 2024, there is another total solar eclipse that will be visible from the U.S. This time, instead of coming from the northwestern seaboard and going to the southeast, this one comes up through Mexico and goes across the central portion of the U.S. Unfortunately, it misses Tennessee, but you can't win them all, right? But it goes up through the northeast. But we're not too far from that path of totality. So if you miss this eclipse, in 7 years, it'll be just a couple of hour drive. You'll be able to get the opportunity to see another total solar eclipse. And there's one little city right up in Illinois called Carbondale. They're actually in the path of both of those eclipses. Okay, so they got really, really lucky. So let's talk just a little bit about the different types of solar eclipses. So most, if not everybody in this room has seen a partial eclipse. Okay, this is where the sun is partially obscured by the moon. Good name. Okay. Total solar eclipse, we're definitely going to focus on that tonight. I'll show you what an annular eclipse is. And then we'll mention the hybrid eclipse as well. These don't happen too terribly often, but it's pretty interesting, the requirements for this type of eclipse. We'll also mention lunar eclipses while we're there. We'll talk about the partial, the total, and the penumbral lunar eclipse. And before we move on to that, let's go back to this figure. So even though the sizes aren't represented correctly, one thing that is depicted pretty well in this diagram is that the shadow of the Earth is much larger than the shadow of the moon. Okay, in reality, that is true. So it's much easier for the moon to pass into a shadow of the Earth than for the moon or to cast a shadow on the Earth. All right, so the point here is that it's much easier, or more common, I should say, for a person to witness a lunar eclipse. Okay, the requirements for this, for the sun, the Earth, and the moon to be in pretty much a straight line are not as stringent for a lunar eclipse, because the moon could be up a little bit higher or down just a little bit lower and still hit at least one of those shadows. All right. So here's a sequence of images of a total lunar eclipse. So like a solar eclipse, like our total solar eclipse, we will have the opportunity to witness a partial solar eclipse before the total solar eclipse. So in this sequence, this was the first image that was taken. The moon is actually in the penumbra, that lighter outer shadow of the Earth, or this portion of the moon is. But this portion of the moon is now within that umbral shadow of the Earth, that darker inner shadow. So if I was standing on the moon here, I would see the sun totally blocked out. Here, I would see the sun partially blocked out. And then a little while later, as the moon continued on through its orbit, the entirety of the moon finally passed into the umbra of the Earth here, and also in this image here. These two images are different just because of the exposure level. One thing that you do notice about a total lunar eclipse, and sometimes a little bit of a partial eclipse, is that the moon will have kind of a reddish hue on it. So the Earth has an atmosphere. Red light passes much easier through our atmosphere than blue light, okay, which is why sunsets appear redder. The blue light actually gets scattered around more, and that's why our sky is blue. It's not because of reflections of the ocean or anything like that. It's actually because of the way blue light interacts with our atmosphere and gets bounced around. So the red light, as it's filtering through our atmosphere, makes it through our atmosphere pretty well and continues on, and some of that lands on the moon here to illuminate it. So if you could look back at the Earth during a total lunar eclipse, you would see the Earth silhouetted, but surrounded by this bright orangey red ring. You would essentially be seeing every sunrise and sunset at the same time on the Earth. Okay? The penumbral eclipse, you might have seen this and not even realized it was happening. They're not that dramatic. So this is a typical full moon. Here's a full moon going through a penumbral lunar eclipse. So this top portion of the moon was just passing through that lighter outer shadow, and you notice that the moon didn't darken dramatically. So these can kind of be hard to spot if you don't know that they are occurring. All right, so enough about the moon. Let's move on to the sun here. Like I mentioned before, we will also have the opportunity to witness a partial solar eclipse on August 21st. In this sequence of images, the observer did not get to see a total solar eclipse. So at maximum eclipse, only this portion of the sun was blocked out. So this may have been about 30 to 40% of the sun was obscured. When we observe our eclipse on August 21st, hopefully there won't be any clouds, so we will get to see it. We'll see the moon coming across, and it'll take a bigger and bigger and bigger chunk out of the sun over the course of an hour and a half. All right? So we'll get to see the partial eclipse before the total eclipse, and then a partial eclipse after the total eclipse. So this is a nice close-up view of a total solar eclipse. The imaging that was done on this required kind of a high dynamic range to bring out the more subtle details. But this image is really great in that it shows you that the outer atmosphere of the sun, what we're seeing here is this white wispiness. This is known as the corona, and that corona is not just a blob. It has structure to it. The structure of that corona, you can see up here, it looks like little hairs sticking out straight. Down here, and then over here you kind of see, looks kind of like a flame shape there. So that structure is caused by the magnetic field of the sun. So the sun has a magnetic field. It's not nice and neat like the Earth's magnetic field. So if you've ever seen pictures of a bar magnet with the magnetic field lines drawn out, you have these lines coming out of one end of the magnet, looping around and going into the other end of the magnet. For the sun, it's not that easy. The sun, being a big ball of gas that's rotating at different rates depending on where you look on the sun, that magnetic field gets really twisted and complicated. Now, towards the poles of the sun, you see more of that simpler structure, the magnetic field coming out of one end and trying to come in to the other end. But out here, you get these really complicated lines where the magnetic field lines are interacting with one another as the sun's rotating at different rates. It's a little bit hard to see, but you notice that the moon here is not totally black. you can start to pick out some very faint features of the moon here. So when we have the moon in a new moon phase, and if we were standing on the moon looking back at the Earth, we would see the Earth in a full phase. The Earth has a lot of clouds. Those clouds are very reflective. Those clouds are really good at reflecting light back to the moon to create a phenomenon known as Earthshine. And so some of that light is illuminating the surface of the moon. It's actually very hard to pick out those details, even when we don't have the eclipse going on here. You can see that Earthshine when the moon has a very thin crescent phase, but it's still hard to pick out those little details. You can tell that it is glowing a little bit, but you're not going to be able to see a whole lot of structure on the moon. This is a really nice view taken back in 2012 of a solar eclipse visible in Australia. So these folks had prime seating here on the beach. I mean, it's nice enough just to be on the beach, but then to be treated to a total solar eclipse was a huge bonus. And again, this photo is not one that's been photoshopped. It may have been lightened a little bit, but this is basically what you would have seen. Right? This is a pretty famous image of an eclipse down in Antarctica back in 2003. The eclipse was occurring at sunset, or the total eclipse was occurring at sunset. This guy here, I don't know if he meant to mess up his buddy's image or not, but he set up his camera tripod right here. So in this image, he's checking the camera. This is his chair. This is his camera bag. So it kind of gives kind of a depth of field, if you will, but I don't know, it'd been nice to kind of have him over to the side a little bit at least. I don't know. But anyway, a really nice image. Now, if you were in space looking back at the Earth, you'd be able to see that shadow very well. So this was an eclipse back in 2016. Here you can see the umbra and the penumbra going across the Earth. In reality, that penumbra extended way up here, all the way down to here. But when you're really close to the edge of that penumbra, of that outer shadow, the amount of shading is very subtle. Okay, so you wouldn't be able to notice it very well in this image. The umbra region is not that entire dark spot. It's just a very central small portion of that dark spot. Okay, so a lot of people in that darker area, like right up in here, they were still seeing a partial eclipse. This is what we mean by an annular eclipse. Now, don't get annular confused with annual, as in it happens every year. Eclipses do happen every year somewhere on the Earth, but an annular eclipse does not happen every year. So annular just means ring. Okay, so annular or annulus, an annulus is just a ring. This type of eclipse occurs when the moon, again, it's in that elliptical orbit, so it's changing its distance, when the moon is near the farthest point in its orbit from the Earth, a point that we call apogee. So if it's farther away from us, it's going to appear smaller, and if it's smaller, or small enough, it will not be able to completely cover the sun here. So these folks never got to see a total solar eclipse. They would never have been able to see that corona in this eclipse. Okay? Any little portion of the sun's surface being exposed would overwhelm that corona. All right, so for August 21st, the entire continental U.S. will have an opportunity to see at least a partial eclipse. In fact, all of North America will have an opportunity to see a partial eclipse. There's a narrow, roughly 75-mile wide band going from the western U.S. to the eastern U.S. where folks can be in the path of totality, where they'll also be able to view that total solar eclipse. Nashville happens to be the largest city in the path of totality, and if you're in the prime spot, you can see up to 2 minutes and 42 seconds of total solar eclipse, or totality. So during totality, you'll see that the sky is going to darken dramatically down to a dusk level. Okay? The temperature is going to drop significantly. In August, that'll be a welcome thing. It's going to be probably going to be pretty hot out there, but the temperature can drop anywhere from 10 to 20 degrees, okay, in a very short period of time. So as the sky is darkening and you start to see that corona come out, you'll also look around the sky and be able to see planets and stars in the daytime. Okay, this will be about 1:30 in the afternoon. And then for the sun, you'll be able to see some features that you normally can't see just by putting on a pair of solar glasses and looking up at the sun. Namely, these things called prominences, and then that beautiful atmosphere that we call the corona. So this is a really nice animation put out by NASA showing that path of totality across the U.S. Now, as the movie progresses, you're going to see these areas that are getting darker and darker in their shading, and then you've got this little spot here that's completely black. So if you're in this black spot, which is tracing out this red band here, you're in the path of totality. You have to be in that red. You can't just be near it. You have to be in it in order to see the total solar eclipse. Folks in this shaded area here will see up at least 90% of the sun covered. Folks in this area here will see at least 75% of the sun covered. Out here, at least 50%. And then folks way up here will even see about 25% of the sun covered. All right? Let's play that one more time here. If I can find my mouse, there it is. Which, by the way, this movie is on our website, so you can get a link to it and download it for yourself. You'll notice the time here. So this starts about a little after 12 our time, 12 noon Central Time. You can see it passes through this path of totality, goes through several cities, just barely hits Kansas City. St. Louis, let me pause this for just a second here. So St. Louis, the northern part of the city is out of the path of totality. The southern part is in. So people are going to be flocking down to the southern part of the city to see it. And then one of the next biggest cities in the path is Charleston, South Carolina. It only takes about 92 minutes for that shadow to go from this seaboard down to this seaboard. Okay, and we're talking about traveling about 3,000 miles here. So the shadow is moving at about twice the speed of sound across the ground. Okay. Here's a depiction again of the U.S. showing that path of totality. The point that we try to really stress to folks is if you want to see this total solar eclipse, you have to be in the shaded area. All right? Again, there's no, I'll just get close to it. No, you have to be in it. If you're just a little bit outside of it, you won't see the total solar eclipse. You'll miss the really spectacular show. In this diagram, the blue line represents where you would want to be in order to get the maximum duration of totality. Okay? That duration varies depending on where you are in this band. So up here, you would only get about a maximum of 2 minutes and 10 seconds. Down here, you would get about 2 minutes and 40 seconds. And a lot of that is due to the curvature of the Earth. Okay? So because the Earth is curving outward, folks in this area are going to be a little bit closer to the moon than folks over here. All right? Just because of the distance, because the Earth essentially over here is curving away. So that makes the moon appear a little bit smaller for them, and so it's not able to cover the sun for as long. So here's a nice blow-up of Tennessee. I'm going to enlarge it just a little bit here. All right. So again, I can't say this enough. You've got to be within this dark purple band and this dark purple band in order to see that total solar eclipse. Franklin is out. In fact, if you get the really high resolution versions of these maps, which there's going to be a little bit of uncertainty. We can't get an exact super precise distance of the moon. The moon has an irregular surface. All these other factors go into determining where this edge of this path of totality is going to lie. But the maps that I've seen, if you go down I-65 to Concord Road, that's where this bottom band is. So this is going to be so August 21st is a Monday. Don't go down to the Cool Springs Mall, waiting for eclipse. You'll see a really nice partial eclipse. The sun will almost completely disappear, but you're going to be just a little bit too far south. Okay? If you can read these contours, so like right in the middle here, so Clarksville is really close to 2 minutes and 40 seconds. Gallatin is in the 2 minute and 40 second band. Lebanon is really, really close to that. They're getting about 2 minutes and 35 seconds, I believe. Downtown Nashville gets about 2 minutes. All right? So not a huge difference. I mean, we went from here down to here and we lost 40 seconds. But if you go from here down to Brentwood, if you were to go to the Dyer Observatory on that day, you would only get about 1 minute of totality. If you went about a mile farther south, you would get about 30 seconds. If you went a little bit farther south, you would be out of the band of totality. Okay? So if you are near this edge, I would encourage you to try to move towards the center. All right? I mean, the closer you are to the edge, if you make just a little jaunt northward, or if you're way up here and you come down just a little bit, you're going to increase the amount of totality substantially. You might triple or quadruple the amount of totality that you'll be able to see. If you're up in Springfield, you know, I wouldn't worry about traveling really. You might gain a second, okay? But we're not doing anything here on the day of the eclipse here at the observatory for a few reasons. One being, we're very near the edge. We're only going to get about a minute. So again, we're trying to encourage folks to go up towards the center of the path, increase the amount of time that you have. 2 minutes and 40 seconds is, you know, hopefully it will seem like an eternity to you. But for most people, it's going to be gone in an instant. In fact, I was reading in the new issue of Sky and Telescope magazine today, there's this thing called Sperling's 8-second rule. There was an astronomer, he was really good at popularizing a lot of techniques and different things in astronomy. His name was Norm Sperling. And he said that, you know, he had seen quite a few eclipses. He said it doesn't matter how long totality is, it always seems like 8 seconds. And so a lot of people adapted that and called that the 8-second rule. Okay? And while I'm thinking about it, don't worry about trying to take images. Everybody else is going to be taking pictures of the total solar eclipse, and all those images are going to look the same. Let somebody else, you know, take those images. Absorb it with your eyes. Okay, really take it in. It's like when we have folks come up to the observatory and see Saturn for the first time in the Seyfert telescope. They've seen really nice Hubble images of Saturn or Voyager images of Saturn, and you know they show incredible detail, but it's nothing like looking in the eyepiece and seeing Saturn for yourself. Okay? So try to absorb this with your eyes. All right? If you want to take pictures, wait for the 2024 eclipse. Drive over to that path of totality and try your camera there. Okay? So for Nashville, and again I want to stress this is for Nashville, because depending on where you are, the time is going to vary a little bit. Like for instance, Clarksville, all of these minutes are shifted by about, or all of these times are shifted by about 1 minute or so. Okay? So for Nashville, first contact, when you have your solar eclipse glasses on and you're watching the sun, when you first start to see a little bite being taken out of the sun, that's at 11:58. By the way, all of this information is also on our website. It's on the sheet that you have as well. Okay? That's when our partial eclipse begins. Now, about an hour and a half later, the moon will have moved its own diameter in its orbit, and it will finally obscure the sun entirely. So for about right around 1:27, and it's going to be a few seconds before or after. It's hard to nail down the exact second. That's when totality will begin. But downtown Nashville only gets about 2 minutes of totality, so by 1:29, the moon will have moved enough in its orbit that the sun will start to pop back out. All right, and totality is over. Fourth contact, that's when the partial eclipse ends. That's when the sun returns to looking like this big ball in the sky. That ends about an hour and a half after third contact. So by 3 p.m., the entire thing's over. So in all, this will take about 3 hours from start to finish. So this is another view from that 2015 eclipse in Norway. If you're closer to the screen, you can see a little spot right there. So that is the planet Venus. This was not a really long exposure image either. So here's a computer-generated view of what might possibly be visible in the Nashville sky during totality. So you've got the sun in total eclipse here. If you look over to the west, about halfway up, you're going to see a really bright object. That's going to be Venus. In fact, nothing else will be brighter than Venus. The only thing that outshines Venus is the sun and the moon. Okay? Jupiter will be in the southeastern sky. It'll be pretty bright, not quite as bright as Venus, but it'll be noticeable. And if you look around the sun, you'll see Mars and Mercury. So you'll be able to see up to 4 planets in the daytime. Okay? Saturn, it won't have risen yet, so don't bother looking for Saturn. You won't find it. You might see a few stars as well, especially the brighter ones, maybe like Arcturus or Sirius. This is also on our website, so you might try to, in a way, try to memorize where things might be. So once totality hits, take a look at the sun, and then look around the sky and see if you can see some of these things. Now for the sun itself, that main thing you're going to be looking for is the corona. You'll see some structure in it. And if you look around the edge of the silhouetted moon, you might see these little reddish pink things. These will be a little bit harder to spot because they'll be pretty small compared to the moon. But those are things called prominences. These are large clouds of hydrogen gas that are being lofted up by the sun, and they're being held there by the magnetic field. The prominences, there's a special type of telescope that you can get. It's a pretty expensive one, I might add, but it will allow you to see prominences on any day. But during the total solar eclipse, when the moon or when the sun's disk is blocked out, you can see those prominences if there happen to be any that day. The only time, though, that you can see the corona is during the total solar eclipse. There's no telescope that will give you a view of the corona. All right? By the way, this corona, this is only about as bright as a full moon. It's safe to look at. When any portion of the sun itself is visible, you have to have protection on your eyes. All right? But once the moon completely blocks out the sun, take whatever eye protection you have on, take it off, look straight up at the sun at this corona. Okay? This will not hurt your eyes. But once any part of that sun begins to pop back out, put those glasses back on. Speaking of bits of the sun popping out, you might see this phenomenon. This is known as Bailey's beads, named after Sir Francis Bailey, who was really one of the first people to report this phenomenon back in 1836. This is especially apparent when you are near like the bottom or the top edge of totality, of that path of totality. The moon's surface is irregular. It has mountains, it has craters, there are valleys in between the mountains. And as little bits of the sun's surface peek through in between the mountains and those valleys, then you'll get this beading effect. You should not look at these beads without eye protection, though. It's going to be hard not to, but don't sit there and stare at them, okay? And the moon is going to be gradually moving, and you'll gradually see these beads changing, okay? If you're more towards the center of the path, it may be harder to see these. But you will see at least one. That's called the diamond ring effect. So this is when the very last portion of the sun's photosphere, or what we consider the surface, it's when the last portion of it is visible. And when there's not enough sunlight to wash out the corona, you start to see it become visible. And so the corona makes the ring, and then that last little bit of the sun's surface makes the diamond. And again, you should not stare at that without eye protection. Speaking of eye protection, we have solar eclipse glasses that we will be able to hand out tonight. We're running low on them, so we'll only be able to hand out one per family. But you only need these during the partial eclipse. The partial eclipse lasts an hour and a half before and an hour and a half after totality. So if you've got 10 members in your family, you've got plenty of time to pass them in amongst the family members. or to hold them up and put your camera up to it and take a picture. Okay? These glasses, some of them tend to have more of a silvery surface on the front here. These glasses block out all of the infrared and the UV light. That's what damages your eye. And it only lets through about 1/1,000,000th of the sun's visible light. So it dims the sun down to a nice level. Okay? If you get those glasses, do not do this. So just for the record, I was not looking at the sun with these. The sun was over this way. But this is an unfiltered telescope, just a regular old telescope. So if you point this telescope at the sun, all of that unfiltered light is being focused down into a much brighter spot. And if you try to look at that with these glasses, it'll still be too bright, and the sun will start to melt right through those glasses. And it doesn't take like 10 minutes to do it. It'll start doing it instantly. And then it starts working on your eyes as well. Okay? So please don't do that. If you are going to do any type of viewing with the telescope, you have to filter the light before it enters that telescope. Speaking of which, telescope companies make solar filters for all the different sizes and styles of telescopes. And again, they're filtering the light before it enters. So I have an example up here if anybody wants to come up and look a little bit later. These have a glass surface on them. So you don't want to really touch the surface, just hold it by the edge. If you lose your glasses or they get damaged and you can't get your hands on any more of those solar glasses, you can use a welder's glass. But the important point here is that you have to have a shade 14 welding glass. You can have a higher number, which just means that it lets through even less light. But if you do a shade 13 or a shade 12, that will not filter the sun's light enough to protect your eyes, and you will get eye damage. Okay? When I've tried to locate these, I've had to get them online or go to a welding supply store. Lowe's or Home Depot tend not to carry specific shades like number 14. I think I only found like shade 5 or shade 10, but they may carry them now. Okay, so don't wait till the last minute to try to get these if you need them. Okay, because you know Ace Hardware or whatever may not have them. If you do get them, one convenient way to mount them and also protect them is just to get a piece of cardboard, cut out a viewing area that's smaller than the glass itself. That way you can lay the glass on top of the cardboard. And here I've taped it so it can't move around or fall off. And when you're holding it up, I would recommend have the glass on top. Okay? You have it on the bottom like this, and maybe you didn't use the best tape in the world, it might end up falling off, and when it hits the ground, it's going to shatter. Okay? So if you hold it like this, then you won't have any chance of it falling out. If you use a box top like this, the box top will also protect it, so you can just lay it down any way, and you won't scratch the surface. Okay? You have to protect these as well. If you scratch the surface of them, that can let through more light and damage your eyes. So we mentioned the solar glasses. If you don't get those glasses, don't get a whole bunch of sunglasses and stack them. This was an image taken during the 2016 eclipse. This is very, very dangerous because even if your glasses say 100% UV protective, they are not going to be able to protect your eyes when you're looking straight at the sun, even if you stack a whole bunch of them on there. Okay? And one of the old-fashioned ways is using exposed X-ray film. I don't know about you, but I don't have X-ray film laying around anymore, so you're probably not going to do this, but if somebody offers it, don't do it, again, because of that whole issue with infrared and UV coming through. And another old-fashioned way of doing it is smoked glass. That's really not good at protecting your eyes from the UV and the infrared. Okay? Hopefully the skies won't look like this on August 21st, but we've all seen, you know, when the clouds get thick enough, you can see that nice ball of the sun. Even if it appears very dim, infrared light, with its lower energy and longer wavelength, is able to get through clouds much easier than visible light. Your eyes can't see infrared light, so you can't detect it coming into your eyes, but it will damage your eyes. Okay? So even though there may be a little bit of visible light coming through, there's a whole lot of infrared and also ultraviolet coming through. I mean, I don't know about you, but I've been sunburned on cloudy days before. So that's just kind of proof in the pudding there that, that UV gets through even the clouds. Okay? All right, now if you do have a telescope, but you don't have a filter for it, you can use your telescope to project the image of the sun. I'll go ahead and preface that by saying don't use a very expensive telescope that you're worried about damaging, because you could damage the scope. All right, so if you've got a little cheap one that you don't mind if it gets damaged, then go for it. So we would have, here's part of the telescope here. This is the eyepiece. This telescope does not have a filter on it, and the sunlight is coming through and it's being projected onto this screen here. This would be safe to look at. All right. Now if you set up something like this, again, make sure you're not using a telescope you don't want to damage, but also set it up so that your screen here will keep somebody from accidentally looking up into this eyepiece. You know, if you're setting this up maybe for like a public display, or you've got little kids around, they may not know that they can't look through this eyepiece up here. So set it up to where nobody can accidentally get to that unfiltered light up here. But again, this is safe to look at. If you don't have a telescope or you don't have glasses, you can use the pinhole viewer method. So you can just get a piece of cardboard, make a small hole in it, maybe about the size of an eraser head, hold the cardboard out. As the sunlight comes through there, the pinhole will project an image onto the ground of the eclipsed sun. This person here used a colander, so you can see that every hole in the colander is actually a partially eclipsed sun. If you're doing this, again, especially if you have smaller kids, make sure they know not to look through the little hole. Okay? Or folks that have never done this kind of projection before, they don't want to look through the hole, they just want to project with it. If you're having a really bad day and you forget your glasses, you forget your cardboard, your colander, your welding glass, I've had those days, right? If you look around at the trees, look under the trees, the holes in the leaves of the trees and the gaps in between the leaves will create little pinholes that will project the image of the sun. Okay? All right, so just to wrap up, the main point that you want to keep in mind is if any part of the sun's surface is visible, so in all of these images of the sun, part of that surface is visible, you have to view with those solar glasses. All right? If less than 1% of the sun's surface is still visible, you will damage your eyes. 1% of the sun's surface is literally 10,000 times brighter than the full moon. Once totality occurs, though, you have to remove the eye protection. If you have your glasses on during totality, you won't see this. You'll just see pitch black, and you'll miss it. Okay? So again, if any part of the sun's surface is visible, have the glasses on. Once you see that last little bit of sun go away, take the glasses off. And once that first spot of sun begins to pop back out, put your glasses back on. Okay? And then finally, if it's completely cloudy that day, you will still get to experience totality, even though you won't be able to see the sun very well. So this was, I believe this was Shanghai during the 2016 eclipse. This is before totality, and then this is during. So you notice that it will darken the sky substantially. So again, even if it's rainy, you're going to experience it. It's going to get really, really dark at 1:30 in the afternoon. Okay? And I think that is about it. So,
we'll take a few questions. I'd like to have whoever is asking the question, though, to ask it through the mic, because we may put this up on YouTube, and that way they'll get to hear the answer and the question that they would like to ask.
Thank you. One thing I've marveled at, thinking about these things over the years, is that that the predictions for all of these different events, including the eclipse, is known so far in the future. Could you just speak a bit to who calculates these orbital motions, and is there an international body that disperses this information, or?
So there are a lot of groups that will that work on calculating orbits. For instance, a few months ago we had Dr. Susan Stewart down here, and she works with the U.S. Naval Observatory, and part of her job is to calculate positions and velocities of, mainly positions and velocities of things like stars and even planets for things like the Naval Almanac. So there are lots of groups that do this. At NASA, Fred Espenak was one of the main folks that really worked on this. I think was he the one that was known as Mr. Eclipse?
Yes.
Okay, thank you. So, I mean, a lot of his job was calculating this, and even though folks are able to calculate these eclipse times very well nowadays, there's still some uncertainty in there. Or I shouldn't say we, but these folks have been able to nail down that uncertainty to a very small amount. But as you go farther and farther out into the future, the uncertainty grows a little bit more. So we can still predict eclipses thousands of years out into the future, but knowing the exact time of day is going to become more and more uncertain the farther into the future that you go.
NASA has the tables for up to the year 3000 posted online, in case they make your lifetime extend, as they say they might be able to. Next question. Okay.
No, you're fine. Only if you want to.
You showed us pictures of an annular eclipse.
Yes.
Is it one also the other way, which the moon is too large and blocks out the sun totally?
So the size of the moon in the sky is going to dictate. I need to move this over a little bit. So the size of the moon in the sky is going to dictate the length of totality. If we go back to this diagram here, you notice how narrow the path of totality is for our eclipse. But if you compare it to some of these other eclipses, like this one down here, this band is a little bit wider. So one of the things that really dictates let me back up. The length of totality is going to be directly related to the width of that band. So the wider the band, the longer you're going to have, or you're going to experience totality. Let's see, where is it? I'm trying to find which one it was. Well, I don't see it. When the moon is near the point called perigee, where it's closest to the Earth, totality is going to be longer. So if you have everything set up just right, where the moon is really close to the Earth, you're in a good spot on the Earth where you're as close to the moon as you can possibly be, then totality can get just a little bit over 7 minutes in duration if everything works just perfectly. Okay? And along those same lines, you'll notice that some of these bands, like this one right here, this almost like a hairline going across there, that one's labeled as a hybrid eclipse. Okay? So for folks that were here, notice they've got a very, very narrow band if they happen to be out on a boat in the middle of the Pacific here. They had a very, very narrow band of totality. So they would maybe see a few seconds of totality. They were a little bit closer to the moon due to their location on the Earth than these folks down here. All right? So for these folks down here, the Earth had curved away enough from the moon that they were a little bit farther away, and so the moon appeared just a little bit smaller to them. So these folks down here did not get to see the total eclipse. They would see an annular eclipse. And so when you have this situation where, depending on where you are, you see an annular or a total, you have something called the hybrid eclipse. So so the closer the moon is to us, the longer the duration of totality. So it's just going to be a nicer eclipse.
So, but would it subtend more of the disk of the sun so that you wouldn't see prominences?
Yeah, that's a good point. So if the moon is larger, let me go back here. So yeah, you would have, so if the moon was really close to you, you would have a longer duration of totality, but it might be harder to see some of these prominences because maybe the moon is completely obscuring them. You might see them right as totality was starting, maybe see these guys over here, and then right as totality was ending, you might get to see some of these over here. But yes, it would make it harder to see things like the prominences.
So that's a very special location to get this figure, this picture, right? You have it exactly the size of the sun.
It's not going to be exactly the size
Well,
of the
I
sun.
mean, very, very close to it.
I mean, you don't have to be in like the exact perfect spot. I mean, you can, in an eclipse like this, I mean, or I should say for our August 21st eclipse, you could be anywhere along that path, and you would see basically the same size moon. I mean, it's not going to change that drastically and really, really affect what you're going to see up here.
Next question. Okay, here we go. Hold on one second.
Can you go back to the slide where you had the north, south, east, and west, and the items? Yeah.
Okay.
Now, if we're facing north, I'm confused as to why east is on the left and west is on the right.
Because you're not reading like a road map.
I was going to say, which perspective is this?
This is if you are, for instance, lying on your back, looking straight up at the sky. Right. So that way, for this room, that way is north.
Right.
The sun rises over here, so that's east. That's west over there.
Yes.
So if you were to basically lean straight back, you would see that north is at your head, your feet are at south, west is over there.
But to me, to me, it still seems backwards. I'm not quite sure how.
It's backwards from what you would see on a road map, because for a map, you're holding it like this. You're basically looking at the ground. But here, you're having to take your map and turn it up like this. Okay. So if I have my road map here, east would be in my right hand, west would be here. Okay, but when we flip it up on the sky, it'll just look backwards.
Unless you're looking through a telescope, then it will invert it. To complicate things.
South will be backwards. It'll just be a mess. Yeah.
Next question.
Let's
Get somebody from the back.
Will a camera be able to see the corona?
So a camera could see the corona. If you want to get an image, let's see, where's a good one here? Where's that first image? Where's this one? Let me go back here. So this particular image, this one took a lot of work. This was a composite of several different images. So you're not going to be able to take your camera and just, during totality, take a quick picture and get an image like that. Okay, you might get more or less something like, where did it go?
And you're not going to have that lens to show that diameter of sun either with your camera.
If you're using something like a phone camera, right, you're not going to be able to zoom in and get an image like that. If you had a nice telephoto lens, you might be able to get an image like that. It also just depends on your level of experience using the camera and if you've done your homework. So there are websites, and even that Sky and Telescope magazine has a nice article talking about if you want to get certain things in your image, here are some settings for your camera. Nowadays, cameras can do things like automatic bracketing, where they're taking different exposures very rapidly, and then you're basically overlaying those. The partial eclipse, you can easily get images of the partial eclipse, but make sure that your camera has a filter on it. So if you're going to use like a phone camera, you can just take your glasses and hold them up and take a picture through that. But it's going to look like a little disc on there. So, don't expect to get, really, really, really nice detailed images unless you have a really elaborate setup. So I would encourage folks to maybe try to take pictures of the partial eclipse. We've got 3 hours of partial eclipse, but don't worry about doing it during totality.
We have people that come to Dyer who spend almost all their time trying to hold an iPhone up to the eyepiece. you know,
Yeah.
when they're seeing Saturn, and that's fine if you want to do that,
Yeah.
except for all the people in line that get frustrated with it. But you know, it's something that when people see a total eclipse and they see the corona, they cry, they weep, they yell, they shout. I mean, it's an emotional experience, and if you're in a huge crowd, it's really amazing. Next question.
Oh, there was a lady up here.
Oh.
I want to have that beautiful experience. The dot on the path of Nashville is totally in the path. Is everybody in the city of Nashville going to be in that path? For example, I live on the western edge of Nashville, in the city, but on the western edge. I don't want to miss it.
So if you're on the western edge, as long as you're not obviously way too far out here, then you should still be fine. Like, I think we've had people from Belle Meade contact us to say, hey, are we in the path? And yeah, those folks are definitely in the path.
But if you're in Bellevue, it's risky.
It's risky. On our website, if you go down, and it's kind of a long page, but we have a section of links. There's one link on, well, let me just go ahead and pull it up here. There's a nice Google map that has been put out by NASA where you can find your location, and it'll tell you the duration of totality, when totality starts, things like that. So let me pull it up here right quick. Where is it? Yeah. So just under the image of the sky, again.
That's backwards.
That's backwards, depending on how you look at it. There is, yes, interactive Google map for totality. So unfortunately, it does not have a place for you just to type in your address, but I mean, you can quickly zoom in here. So for instance, I'll try the observatory. I've never zoomed up maximum. Okay, so we are like right about in here. Okay, so you click there. Tells us we have about 1 minute and 10 seconds of totality. Partial starts at, let's see, that'll be 11:58 our time. The total eclipse begins at 1:27 our time. So this is really handy. It should be fairly accurate as well. Okay, might be a second or two off, but again, there's always some uncertainty in things.
Don't miss it.
Oh, there was. Oh, we have several questions here.
Okay, let me start back here.
Would you be able to look at through a telescope at a total eclipse, but not like a partial?
You could look at the total eclipse through a telescope, but it's very dangerous. And the reason being is if you have a filter on your telescope, you won't be able to see anything. So you'd have to take the filter off. Looking at the totally eclipsed sun with the telescope would not damage your eyes, but it's very risky because you don't know exactly when the first bit of sun is going to pop back out. And even that tiny little bit is going to be able to damage your eyes, especially looking through a telescope, okay, because it's gathering a whole lot more light than what your eye is able to take in at any one time, and so it's going to really put a lot of light into your eye. So I would not recommend that at all. And folks that have seen the total eclipses, actually, where's Dr. Garrison? He's in the very back there. He's one of our volunteers. He's witnessed total solar eclipse. Folks have said that some of the best, or the best views are just looking at it naked eye. Okay? You're not going to gain a whole lot by looking at it up close. Okay?
So if we're going to go like online and buy glasses to watch it, like say Amazon,
Okay.
what am I looking for? How do I know that they're real solar glasses?
Good question. So the first thing I would search for is solar eclipse glasses, and places that sell these, they should have, I think it's an ISO certification.
Yeah, I saw something that said CE and then ISO certified.
Yeah,
Okay.
so that's one of the things that you'll want to look for. But places like RainbowSymphony.com, American Paper Optics, those are two huge manufacturers they're certified. They have great products. I think ours are Rainbow Symphony, aren't they?
Adventure Science Center is selling them as well.
And Adventure Science Center is selling them as well. And there will be some other places around that might be selling them as well. But, I wouldn't go to, like, some little shack off to the side of the road that says they've got glasses. They might not be legit.
Cold Springs.
Yeah, there you go. Yes.
So I never look at the sun, just normal on a normal day.
Mm-hmm.
So, but I imagine it's pretty small at like 1:30 in the afternoon when you're looking up.
Next time you see the full moon, the sun is the same size as the full moon. It looks, you would think it'd be a lot bigger just because it's so bright and there's a lot of glare.
Okay.
But if you take your pinky nail and hold it out at arm's length, your pinky fingernail is about twice as wide as the sun.
Okay.
You'd think it'd be a lot
So
bigger.
it's a little thing up
It's
there
a
we're
little
looking
thing,
at.
yeah,
Okay.
yeah. I think we have
One thing about the Eclipse glasses, if you buy them and they get a little pinhole or a scratch, don't use them. So that's very important. Okay, question back here.
I know we were making jokes about the Cool Springs thing, but do you know if there's going to be any traffic regulations on the day of the eclipse, given all of that? You know how like the city is responding? Because I know metro schools are going to be out the day of because they don't want to take liability for it.
Right, and that's been a big discussion point. So if you're going to be going anywhere on Eclipse Day, like if you want to travel north, do it early in the morning. So Nashville is expecting at least 1 million people to be coming in to view the eclipse. Okay.
You can't find a hotel room at this point.
Right.
Yeah, and some have said 2 million in Middle Tennessee.
And if you think about it, so if we look at this map here, the path of totality goes right over where 3 major interstates come together. So at 1:30 or 1:27, whenever totality occurs, the interstates, you can bet, are just going to be completely at a standstill. People are probably going to be getting out, walking around, looking at this. You can think about it, a lot of people are going to be coming through just, maybe as part of their job. They don't know anything about the eclipse. All of a sudden, it gets dark, and then it gets really dark, more than what, any cloud is going to be able to do. So, right. So the police, obviously aren't going to want you to stop, but, you can bet that everybody's going to be stopping. If you're going to be traveling that day, I would recommend doing it early or do it the day before if you're going to go stay at a friend's house. Don't think, oh, I'll leave a couple hours ahead of time, because it's going to be packed. There's going to be activities going on downtown, especially if you're going to be heading in the downtown area. There's maybe roads closed because of activities. And don't expect to get back home maybe till late in the evening.
And take water with you and your Eclipse
yeah.
glasses, because you may be watching it from the side of the road.
Or your colander or whatever you want to use, okay? Yeah, she's got one here.
Where are you going to watch it?
I don't know where I'm going to watch it yet. I'm going to try to head, so I live over in Antioch, and I'm kind of greedy. I want to try to get as much eclipse time as I can, so I might head over towards Lebanon somewhere. I'm not really sure yet.
Okay.
He's not going to tell you because he didn't want you coming there.
You're not supposed to tell them that. I think we had one question up here.
Okay.
I can talk pretty loud.
Well, we want the camera to get it.
Yeah, the camera's got the input on it.
Is there a good way, similar to where you're doing a pinhole projection with a telescope, where you're projecting it out, to do something that's live, that you can get a bigger image of the total eclipse?
So one thing you can do, just using the projection method, let's see, where is it? So if you're careful in how you set up your telescope, so that folks can't accidentally look into the eyepiece, then you can move that projection screen pretty far back, and if you have some sort of enclosure around it, we did that for the Venus transit back in 2012. And I had the projection screen about this far back from the telescope. It's also going to depend on the eyepiece that you use. But I had an image of the sun about that big, and it was in an enclosure, so it was easy to see. And the farther back you move it, the bigger it's going to be, but the fainter it's going to be. So yeah, if you can just get a nice dark enclosure, then that should help you out a lot. Some folks also do something called a sun gun, where it's basically a funnel, and you can find instructions online, and they put some sort of translucent material. It could be like a type of rear projection screen material, or you could even get like a piece of white fabric and put it on there, as long as it's not too thick. And you can project the image onto that, and people just walking by can look straight at that. And there's no way that they can look into the telescope, because the funnel actually fits onto the eyepiece, so it makes it much safer as well. I think we have that online on our Dyer webpage as well. There's one thing I forgot to mention that I thought folks might really think was interesting. I think I put it in here. Maybe I missed it. So this eclipse is going to be pretty special for a number of reasons. It's the first time a total solar eclipse has been visible across the U.S. since 1918. It's the first time a total solar eclipse has been visible from mainland U.S. since 1979. There was one where the totality path went up this way. First time since 1991 where a total solar eclipse was visible from U.S. soil. And that one actually, that path passed over Hawaii. First time Nashville has had one in 539 years. The next one, total solar eclipse for Nashville, will be in 549 years. Okay? On average, there's about 360 to 400 years between times when a total solar eclipse is visible from one area. We'll have plenty of partial eclipses in between now and then, but to see the next total solar eclipse, again, you're going to have to wait for about 539 years.
Yeah, so imagine if you were 1 mile off the path of totality.
Yeah, you'd really be kicking yourself. But going along the lines with that, eclipses aren't that rare. So I showed you the at the beginning here. So this was, yeah, here we are. So this is the years 2001 to 2020. You can see the different paths here. So there's a number of paths. And again, the ones in blue, this is 2021 to 2040. The paths that are in blue are where you see the total solar eclipse. So you'd think it'd be pretty rare. But here is a map for the year 1000 to 2000. Let me bring it up here. So that's that same map showing the path of every total solar eclipse from the year 1001 to the year 2000. So you can see that, you know, basically the entire Earth is covered in this view. Let me zoom over.
So imagine if you lived in that one little spot.
Yeah.
So you waited 1,000 years.
Yeah, some of these people over here in Nebraska, they're really sad, and Indiana over here. So maybe in the next 1,000 years.
Let's take one more question. And then the telescope is open, isn't it, Dr. Bob? We have Jupiter. How's it look tonight? Okay, good. Who's going to have the last question? What lucky soul? Who has a great question? Of course, usually people that ask it don't know that it's a great question. You look like you'd have a great question.
So if these things have been blue for thousands of years, what thousands of years did people think when that sun got so dark? I mean, did they think the world was done? We're done?
Yeah, so a lot of cultures, I think it was the Japanese, whenever there was a partial eclipse, one of the things they would do was shoot flaming arrows into the sky. A lot of cultures actually did that because they thought that it was some sort of creature that was eating up the life-giving sun. So they would shoot flaming arrows, they'd bang pots and pans, just try to scare it off, and it worked every time. Yeah. So that goes along with what Rocky was saying. Folks get very emotional during a total solar eclipse because there's nothing else like it. I mean, we've all seen beautiful sunsets, but this is totally different from that. So.
Read A Connecticut Yankee in King Arthur's Court.
Yeah.
So for every family here, we have eclipse glasses. Just one pair. We're running kind of short. But as you go out, we will make sure that you get one. I'll be standing out there at the box. So please, let's limit it to one glass per family?
I think that we have enough for every family to get one of the little baggies. It has the Eclipse glasses in there, and it has the really quick and dirty version of the information that you need to know for the Eclipse. So it'll have a little bit of the map on the back, when to use the glasses and when to have the glasses off, as well as what you can see around the sun during the total eclipse. Even has the eclipse times. So our admin assistant, Alex, who's not here tonight, put all these together. She put all of them in the bags together, too.
And if you have more questions, Dr. Billy will be around. Thank you, everybody.
Thank you.